Hey guys, I hope the coding for principal component analysis is coming well. In this video, what I'm going to do is I'm going to share with you some tips and techniques that you can use to implement principal component analysis. To be very frank, principal component analysis involves calculations, a lot of calculations of a lot of statistical parameters, and then finding their then formulating a covariance matrix, and then finding the eigenvalues and eigenvectors, and use the eigenvalues and eigenvectors to draw the axis on the objects. Now, the statistics that you generate for different objects in an image or in your data in general are going to be used for performing some sort of classification. So let's get into what specifically you need to perform in principal component analysis exercise for your exam number 2. So the goal of the principal component analysis in exam number 2 is to detect different objects. We have three specific classes of objects, and those are apples, bananas, and tangerines. Using the objects in the very first image, fruit1.bmp, you are going to extract the statistics of these individual objects and then perform the model construction, which is going to identify fruits in image 1 as well as fruits in image 2 properly. Now, the word model construction becomes a little bit more complicated because the industry and academia in general have glorified the word model so much that it almost seems like an extremely complex entity. But honestly, the statistical model that you're going to design in this case is nothing but just a bunch of if and else statements that compare the statistics of a given object with predetermined statistics of the already detected objects, so that to find out whether an object belongs to a particular class or not. So let's get started into what essentially you'll be doing in the principal component analysis section of your exam. So first things first, you're going to try your code main.m using the image fruit1.bmp. So in the files that I have given you, there's going to be a file called main.m. This is the primary file which you are going to run. So once you run this file, it's going to produce a bunch of images as well as a bunch of data for you. If you notice the workspace, when you run main.m with fruit1.bmp, you'll see the several variables created like num components. You'll see variables like labels. You'll see variables like capital L and small f and several others. The variable num components, it tells you how many possible fruits are present inside of an image. For fruit1.bmp, you'll find that the number of components, num components, is equal to 20, which means that my image processing algorithm has identified 20 tentative objects which can be fruits, and it's up to us to teach computer how it can detect the specific fruits in the image. Now remember, out of these 20 labels, not all of them are fruits. Only 6 objects are fruits, and we need to focus on the statistics of only those 6 objects. Next, what you need to do is calculate the statistics, meaning moments and central moments, m's and mu's, for all of these different 20 components. Now, in how to compute those moments, what you need to do is go back to the handout that I have given you for principal component analysis, and there I have mentioned all the formulae for you to use to calculate the moments m and central moments mu's. So you need to calculate m11, you need to calculate m11, you need to calculate u01, u02, u20, then u11, and xc and yc, and along with that some other statistics you can also generate that can help you with the object detection. Okay, so this is what your part 1 essentially is going to look like. Part 1 is just implementation of those formula, but you need to use some sort of a programming construct here to evaluate the statistics for different 20 components inside of fruit1.bmp. So your pseudocode, your part 1 pseudocode is going to look something like this. Now, pseudocode is pseudocode. It's not an actual code that you can use directly in MATLAB. You have to convert the pseudocode to MATLAB, and this is how the pseudocode is going to look like. So for label, in my labels, So you need to set up a for loop, and you will use an iterator that is going to go through each of the labels in the labels, which denotes what specific label values the different fruits are or different objects are getting. You'll find that the labels are 10, 20, 30, and so on until 200 for those 20 objects. So there's going to be an object with label 10, there's going to be an object with label 20, and so on and so forth. I can tell you for a fact here that in fruit1.bmp, the label 20 is for the banana, which is sitting on the top left corner of the image. So for label in labels, here's what you're going to do. So for XY coordinates or for XY locations in F, you're going to see if f of x comma y is equal to this label. If it is equal to that label, then you are going to aggregate you are going to perform the computation of the moments and central moments and what have you. So, and it will take something like this: m00 plus is equal to something, because you're performing the aggregation, you're performing that double summation over x and y. You will have m11 plus equal to something, similarly u20 plus equal to something, and so on and so forth. My recommendation is for these statistical values, use some sort of an array. For example, I would use an array of size 20 because I have 20 components, so that I know that for which particular component I'm computing the corresponding moments or central moments. So I'm going to use some sort of an array which has the same size as the size of the labels. So use arrays to store statistical values for use arrays to store statistical values, and the size of these arrays is going to be same size as labels, meaning 20 in this case for fruit1.bmp. So your for loop will look something like this: m00 of label plus equal to something, m11 of label plus equal to something, and similarly mu02 of label plus equal to something, and so on and so forth. So in this way, you would have computed the statistics, moments and central moments. Even if you want to calculate other things like eigenvalues and eigenvectors, you would have calculated for all of these guys, for all of these objects, all of these 20 objects in the image. So that's your part one, where you are performing just math computations. It's as boring as doing simple calculations on pencil and paper, just that you're performing or you're having your computer to do it. So that's what part one is. It's just a bunch of math computations. Then between part one and part two, you'll perform statistical analysis, which I think is more interesting than part one. So you're going to perform statistical analysis, wherein you will specifically observe the statistics for the fruits that you as a human can see in the image. So I as a human can see that there's a banana sitting here, then there's a banana here, then there is an apple here, then there's a tangerine here, then there's another apple, then there's another tangerine. Now these different objects will have different labels. For example, I told you that this banana has label equal to 20. Similarly, this tangerine will have another label, which you need to find out. Similarly, this banana will have another label. To identify what labels are given to these individual objects, I recommend the use of a function that I have given you. It should be in your files that you downloaded. It's called pixel capture. So using pixel capture, what it is essentially going to do is it's going to activate some sort of a crosshair. It's going to activate some sort of a crosshair, which you can place it in a particular location and click enter, or just click it. So MATLAB is going to tell you what label does this pixel have. And that will be the label for all the pixels or all the constituents of this particular tangerine. Similarly, you can find the labels for this tangerine, for this apple, for this banana, and so on and so forth. Once you have identified the individual labels for these different objects, you are going to find out what kind of statistics were produced in part one for these objects. For example, m00 of 20 is going to tell me it's going to tell me what M00 statistic is for this particular object, because this object has label 20, so I can use an index 20. For your programs, there may be better ways of indexing these individual objects, not necessarily 20, but some other ways of accessing the labels of these guys. So you are going to find out what kind of statistics were generated for these individual objects by querying their individual labels. And then you'll sit with your partner and write it down in an Excel sheet, maybe like for apple 1, for this particular apple, for this apple, what were the statistics? How were the stat values? It must have gotten some M11, let me call it M11A1 as the first XY moment of apple 1. It may have gotten some mu02, it may have gotten some mu20, it may have gotten some mu11, it may have gotten some value of eccentricity, and so on and so forth, and some value of lambda 1, some value of lambda 2. And these are all the statistics that you need to generate for each object in the image. So these are the statistics for apple 1. Similarly, you'll find out what are these statistic values for apple 2. You'll notice once you enter them in an Excel sheet, you'll notice that these two are quite similar. They're not same, they are similar. They will have similar range of values. Similarly, you will find that tangerine and tangerine 1 and tangerine 2 have similar set of statistical values. Not same, similar. Similarly, banana 1 and banana 2 are going to have identical or other similar statistical values. So with your partner, you'll find out the range of statistical values for each of these individual fruits. So there's going to be a range of values that an object can satisfy for it to be classified as an apple. So that range of values can be like something like, I don't know, there will be some range of statistical values essentially. So similarly, you'll find the range of statistical values for the two tangerines, you'll find the range of statistical values for the two bananas. Then comes, after you have identified the range of statistical values for those three fruits, next comes the modeling, the statistical modeling. As I mentioned before, people in industry have glorified this word model so much that it seems like a very complex entity. Actually, it's not at all complicated. It's not complicated. In this case, it's going to be just a set of if and else statements. For example, when you want to classify a particular object in another image, you will again generate the statistical values for those objects using step 1, and then finally in step 2, your model will essentially look something like this. If an object has, let's say, M11 that falls within a range for apple, and let's say mu02 falls within a range, and so on, then it's going to be an apple. Else, you're going to compare it with the statistical range of values for, let's say, a banana. Else, you'll check it for statistical value, or you will check it against the range of statistical values for a tangerine. If none of these satisfy, then else it's not an object. It's not an object that you're looking for. This is the statistical model that you'll be devising in step 2. You may not be using these exact statistics, but you will be working with your partner to decide what statistical values truly differentiate these different objects. What statistical values differentiate an apple from a banana? What statistical values differentiate an apple from an orange, and so on and so forth. You are going to sit with your partner and decide which statistical values you are going to use in these if conditions. That's your statistical model. And that's it. You're going to try step number 2 on fruit1.bmp, and to make sure that you are able to draw the axis on these objects properly or not. Once you nail down the overlaying of the axis on these objects, then you can move on and try your entire code with fruit2 to see if your object recognition is working properly or not. So that's essentially what you need to perform in principal component analysis part of quiz number 2. As I mentioned before, step 1 is just mechanical calculations where you are getting a bunch of moments and central moments and other statistics for different components or different labels that were generated by your program, where each label corresponds to a particular unique object. The next intermediate step is statistical analysis, where you will sit with your partner and enter the statistical values inside a nice Excel sheet to understand or to study how an apple is shaped, how a banana is shaped with respect to these statistical values, how a tangerine is shaped. Then you'll determine the range of values for apples, bananas, and tangerines and implement your statistical model, which is just a set of if-else statements that uses statistical values of your choice, that uses statistical parameters of your choice that you decided with your partners to detect objects and classify them as either apple or a banana or a tangerine, or classify it as not an object. Should you have any questions or concerns with the coding aspect in step 1 or drawing of these lines, please let me know on Slack channel. And I'll be happy to discuss with you on the Slack channel. Okay, I think it's a good time to stop this bonus lecturette right here.